Welcome back, everyone. So now we have reviewed what embeddings are, sentence embeddings are. We also know what a BERT is, or what a vision transformer is, and so forth. We also know about contrastive loss. These are the three things we reviewed just a little while ago. Now we are going to cover this paper, the clip. It's a landmark paper, as I said, because in a way it opened the door to multimodal learning and was one of the key papers in the development of visual language models. So I'll just do a very quick recap of some of the things that we have been talking about. We said that suppose you had a machine, and by the way, now I'm going to generalize. I'll just use the word encoder. And I had an image of a cat. Here's a cat. And I could send this image in. Somehow, it doesn't matter how, but somehow I could get a latent representation, some latent representation vector of the cat, of this image. Then it may be whatever it is. Now, we realize that I can always align this vector to be what I want. For classification tasks, I could use, for example, if I'm classifying between cats and dogs and horses, I could use a classifier loss function. Right. But one question that you can ask is, if we played this thing with games, with words, that the words could have a contrastive loss associated with them, text could have contrastive loss associated with the output. Like if this output you fed into a contrastive loss function, what did it do? And with triplets, namely the x, the similar, given a reference vector, hx, you take a similar vector and you take a completely random vector. You want to maximize the similarity or minimize the distance between the hx and hs, and you want to maximize the distance, or rather minimize the similarity between these two, right? So when you do that, that is called contrastive learning. Let me just call it contrastive learning. Because then what you're doing is you're training the machine with a different loss function. And so for the same picture, a different kind of output vectors will start coming for words. Now, this paper asks this question. See, look at the sentence encoder, for example. There, the triplet was H, similar, text, and a random text. These were all text, text, text. Isn't it? That's how we did it. But what if we could do something interesting? What if we could take an image instead, replace this with the image of a cat, right? We replace it with a cat. And what if this similar thing was cat on the windowsill? Let's say suppose this was the text. Now you say, well, and then this doesn't matter, just some random text. Now you say, well, how is that possible? Well, we said it's quite possible because now you don't compare these three things. What you can do is this will somehow become hx, and now we know how. You can use a visual encoder. So one visual encoder is the VIT that we learned about. The other visual encoders, actually, the more historical ones, are CNN based. So for example, you could take any convolutional neural net. What do they produce at the final layer? After the convolutions and you feed it through a feed-forward layers, which do the transformation, you flatten it out. It again becomes a vector, right? That is also a hidden representation of an image. It doesn't matter how you produce an encoding of an image to a vector, but you can produce that. And suppose you take that here, and then the text, the similar text encoding is quite easy. You get this, and then this is easy. So you can still play your contrastive learning game on this. Does that make sense, guys? You can do your contrastive learning now on this. Right? The key bridge is you just need a visual encoder. You can use a CNN-based architecture, or you can use a transformer-based architecture. Right? And so this paper says, I'll take questions. So in a moment. So this paper says, what if we just put contrastive loss on a visual encoder, bring these two ideas together. So the two big ideas, and I'll just bracket it out as a milestone here for us. Visual encoder plus contrastive learning. Yeah. Then what it would mean is, so long as you can produce this vector, you realize that the rest of the learning is exactly the same as what we did with sentence embedding, isn't it? In other words, you can project it down to a vector space, a latent vector space, H, belonging to whatever dimension, latent dimension D, where suppose the cat vector lands here and there are texts around it. What will be the text around it? It would be textual descriptions of the cat, isn't it? In fact, this embedding space has no way to tell whether that point originally came from an image or it came from a text, isn't it? Because a vector is a vector is a vector. All you get in the latent space are the vectors. Does that make sense, guys? And so that whole approximate nearest neighbor technology that you are familiar with, you can reuse now for images too in your mix. Make sense? Right? Yeah. Okay. So guys, I know you have questions, but follow through with the argument and then I'll take questions. We can embed, therefore, images and words into the same space. And the moment you realize that we can do that and give it meaning, it's a different question. How do we produce this data? That's a serious question. But at least in principle, if we could do that, we will be able to use text to search for images, images to search for text, images to search for images, right? All of those combinations become possible. Or given a query vector, given a query, suppose the query is a dog running after the ball. This can easily map to a vector, which if you do a similarity measure in this vector space, in the latent space, it can bring other vectors, retrieve. So a search in the embedding space can bring other vectors, let's say HA, HB, HC, similarity vector, similar vectors. They could be text or they could be other images of dogs, a dog running around, isn't it? Does the idea conceptually make sense? Right? So that is the key insight of this paper. But it begs the question, and we'll go over this image here, which is really the main thing. So let me go over this image for a moment. Why am I not able to touch on? Okay. Yes. So let's pay attention to this image. What we are doing, if you look very carefully, what we are doing is we are taking a picture of a dog. Now, a dog picture is an RGB channel, but let's ignore the channel part. You take a picture and you have many pictures here. Any one picture, so let's say this dog, I can encode it as this vector, image vector, right? In our notation, we will call it the H of the dog, right? The image vector can be encoded. In the beginning, machine will just encode it to some random vector. right? With random values. Likewise, for text, we can use, now suppose we can use a properly trained text encoder, right? How do we do that? We already know how to do that. So you can take a pre-trained text encoder, or if you want, you can sort of let it also get trained. I think in this, they just take a text encoder also, and they say we'll train it also jointly, right? So you take a text encoder, for example, your standard BERT encoder, completely untrained. You just take it. You give it a text. This is the text. Now, what do you expect? You want that if these two texts are aligned, if they are talking about the same thing, then these two vectors should land in the vector space very close to each other, isn't it? So one way is that their dot product or their cosine similarity should be high. Right? Dot product or cosine, right, is a measure of similarity, which is this diagonal. If it is normalized vector, then this is a cosine. But you get the cosine out of the diagonal. You want this to be high, similarity to be high, isn't it? And you can train the machine to do that, isn't it? And so the statement that is here, let's read this. Summary of our approach. While standard image models jointly train an image feature extractor and a linear classifier to predict some label, some label. So that is the normal VIT, etc., that we went through, or ResNet and whatnot, any of the CNN based. Read this sentence. Clip jointly trains an image encoder and a text encoder to predict the correct pairing of a batch of image text training examples. So here, the main thing is that you have image, text. This is it. And what you try to do is that you try to maximize this similarity, or sort of minimize this distance. Yeah. Right. Now the question remains, how in the world do we get such data? Right? Images and their descriptions, will come to it. At test time, the learning text encoder synthesizes a zero-shot linear classifier by embedding the names or descriptions of the target datasets class. So, I mean, later on you can encode it and see what image it matches to. But let's go back to the main idea here. I'll just shrink it again. And the biggest problem here is how in the world, and so now let's go back to the name of the paper. It will make sense. Somewhere they introduced the word clip. See, so remember, this paper was written a while ago, 2021. At that moment, CNNs were, and even now, are still quite heavily used, but perhaps not as much as then. It talks about AlexNet and ResNet and so forth. And VIT had just made its appearance on the scene, and people are beginning to use it. So I think approach, here it is, selecting an efficient pre-training method. So they clip, somewhere they say this is what we call clip.
It's the last paragraph on the right on page 2.
Last paragraph on the right on page 2. Right.
Contrastive
somewhere it clip. We call clip, yeah, for contrastive language image pre-training. Right? So that's where you're using a contrastive loss function. That is it. Now, one question. So there is not much to this. If you notice, this picture is more about, okay, we did this, we did that, and how this is how we trained, and this is a large data set, and blah, blah, blah. So it goes, I mean, those things. Today, this code says it all. Like you take the image, this code, if you look at it, it says image encoder can be a ResNet or a vision transformer, right? A text encoder, use any text transformer, right? Remember today, like for example, it says use any word embedding or text encoder, text transformer, right? A CBOW is Right? It is a word-to-vec approach. Right? Do that. And after that, the rest of it is just a mini batch of aligned images, mini batch of trained images, etc. You set it up, you normalize it. So when you normalize it here, you basically are saying, I am going to, you're basically doing cosine similarity. You notice that you're doing dot product between these two vectors here. And when you normalize that, L2 normalize it, what do you mean? You scale it by their sizes. You're basically looking at cosine similarity. So this is it. The logics are nothing but the cosine similarities of which get exponentiated and so on and so forth. Loss is, now you can look at the loss, just as you would expect the loss to be. So this code pretty much says it all, what we have been talking about. Nothing unusual here. Now, one question that it leaves, where do you get a vast repository of labeled images? Because what you need is a text and, an image and a good caption for that or text for that, describing that image, right? So the whole question is, now where do we get a gazillion of those? Yeah, no. Well, that's not big enough, right? So what they did is something pretty clever. You scrape the web. When you scrape the web in the HTML, those of you who remember your HTML, you often say image src is equal to, let's say, dog.png, some picture, right? And then you also give sometimes the alt is equal to blah. Do you remember the alternative? You describe what the image is, right? The text. And so if you scrape the web, you will get a lot of noise because most people forget to put the alt, right? So those are the wastes. But quite often you will get a dog and alt, a text, a picture and a text there. And so they form your pair, right? That is what they trained on. One of the things they realized when they trained on this was that this data is very noisy. There's no doubt about it. Because what people do is, those of you who are into search engine optimization know that what this software tools do is they try to sort of hack Google search. So what they do is all the ads will be filled with buzzwords, keywords to increase their search results. Right? Yeah. So you won't really find a lot of meaningful text. So there is a lot of noise in the data, but still they managed to scrape enough of the data from the internet that they were able to train CLIP very well. In fact, if you go back now and look at the Jupyter notebook, which was for search, you remember we looked at the dog, the golden retriever, the search. And if you look very carefully, what is the encoder we are using there? You will realize that we are using the CLIP encoder, literally the result of this paper. It is the CLIP encoder we are using. So that is the whole picture, guys. That's the whole story of this. There isn't, this is all that this paper is about. I'll let you read it. It's quite effective. And it does produce very good results. In fact, today, no, we don't question it. All we do is we improve upon CLIP. There are many things that can improve upon it, right? But CLIP has become sort of the default thing. Is it used? Massively. If you work in any one of the places which harvest a lot of images or do a lot of image processing, photo sites or video sites or social media companies, this opened the door to indexing and searching images now based on the meaning of the image. You see that, right? You could say, show me all the dogs. Something that wasn't quite possible, right? You could do image searches. And what is more, it opens the door to many, many useful things. You know, if I have a picture of you, now I can search for all similar pictures of you, things like that. So, yeah, go ahead.
Say you have like an invoice and you're trying to scan it in a sense an OCR, but you're trying to get more information than just the text. Is there a point where we're doing more or different models in order to be able to obtain that, or does some of what we're looking at right now fall within that realm?
No. In this particular workshop, we'll devote literally 2 weeks to document AI, and we'll develop this idea. So this is the beginning of the idea. We are going to develop this idea much further. The state of the art is that you can ask what, given an invoice and an image, you could literally ask it questions like, is this invoice paid or not? Or you could ask, what was the total? Or is there error in the totaling? Or things like that. So the state of the art has advanced quite a bit, and it is part of this bootcamp. We'll come to it, but that's for much later.
Thank you.
Okay, I had questions, and then I'll start with some questions that were waiting. Some guys there, yeah.
So on your writings,
Yeah.
you create the image filter.
Yes.
So on the random you put text, but the search and the reference was image. It should be homogeneous, or I can.
No. You focus on an image and a text, and the third part, you just put whatever you want.
It could be anything.
Yeah. Generally, text is far cheaper than images. So you just take a random text.
Okay, and then the second question, I'm sorry, follow-up question. So the encoder part,
Yeah.
so that is pretty much with the what other encoder we can use? Because sentence would be like a word encoder or
Yeah. Theoretically, any box that will convert an image into a vector will do.
And then plus the contrastive last function.
Yeah.
So how do we do that? Okay, so is it going to be simple math or is it
just math? It's just math. See, remember, what is machine learning? So this is a very good question that Ganges asked, that how does this magic work? Right? See, first step, remember that the core learning loop of machine learning is, especially with neural nets, any neural net, is just the four things like that. For some epoch, you're in some epoch of training, you iterate through the data. For some mini batch, so here, what do you have? You have a little mini batch of data.
Yeah.
You do one forward pass, which in your case is, you give that image or whatever it is that you want to give, and out will come, in this particular case, your hidden state. Right? Now the problem is, the second step always in machine learning now is to compare it to what you want it to be.
It's last.
Right. So you compare. So if we, in more common language, if we call it y hat, you need to feed that y against the ground truth to get a loss function. The third step is backprop and compute all the gradients, right? For every single parameter in your system. And the fourth step is, of course, the learning step. All the weights go to the previous value of weights minus alpha, gradient of the loss with respect to that weight. So all of machine learning is that. So now think about it. Within that framework, look at what we do. We have a box, you don't care. It's so long as it is a trainable box. It has to be trainable. You have to be able to turn the dials in that box. Whether it is ResNet, whether it's a CNN, whether it's a transformer, you don't care. You need a trainable box so that by turning the knobs, you can change the output, the hidden state output that's coming out. Right? Then what you do is you need a good loss function. You choose contrastive loss. And then you do the machinery of turning the knobs in the box. What will it do? It will ultimately force that box to produce those hidden states which are aligned with the text, isn't it? That's it. And that is the gist of this paper.
Then like taking to the learning loop.
Yeah. Right. And this is one of the lessons you learn, guys, that a lot of research in our field often comes to the interplay of the loss function. Loss function is at the heart of everything. If you think of a good loss function, right, you already have a breakthrough. Right? For example, Shraddha's paper reading on Wednesday, what did she do? She was looking for, in a nuclear material, in the nuclear fission material, she was looking for these bubbles, these defects, right? And to properly segment those defects, she had to tell where is the defect, what's the boundary of it, and how do you distinguish it from the non-defect, and the degree of defects and so forth. So what did she do? She took the standard cross entropy laws, weighted cross entropy laws, and then she says, well, now wait a minute, we can improve upon it by adding an extra weightage factor. This point matters more if it is closer to the boundary, to the bubble. It matters less if it is sort of in the core of this proper material, right? And so she added extra term to the loss function, right? If you remember, and this is a digression for those of you who can, she added a term which is distance from the, and I'm oversimplifying, Shraddha, please correct me if I'm off, distance from the boundary over what is essentially your cross entropy loss, weighted binary cross entropy loss, right? Which is your log P, right? Or in our language, we would call it Y log Y hat, roughly speaking, right? Weighted by how class weight, right? How often it is. That's all it is, right? So think about it. The cross entropy loss has been known for a very, very long time. You use it for all sorts of classification training. What is the key insight in the nuclear reactor material? That if you want to properly determine or segment out these bubbles, etc., clearly, then be sensitive to, when you create a loss function, give more weightage to mistakes made closer to the boundary. That's all. Right? So loss function is, and constructing and discovering good loss functions for specific domains is one of the core activities in this field. Shraddha, did I get the gist of your paper right? Yes. Yeah, go ahead, Ramji.
One question is like, let's say you take a little more complex example as like a parking lot, where essentially there are several cars, but you're not trying to find a car that identifies the parking lot. So one approach would be, hey, I can feed several parking lot pictures, different signs, and go through this.
Yeah.
But if, let's say, you just hypothetically you don't have many such pictures, you have just one. Is there a way to sort of say, hey, this is my index database, right? Use it as seeds, starting seed into learning. You don't need to learn this, but this is this picture and this is the parking lot. This means parking lot. Is that something possible?
You could do that. You could do that. The only thing is that what would be the error rate if you don't train it with enough of those? Generally, what happens is that generally these things learn pretty quickly these days. One picture may not be enough. I mean, you would have an error rate.
I see.
But it improves as you add more pictures. Somebody there had a question. Anybody else has a question? Yeah, go ahead.
So when we have Google Photos app, like Google or Apple, sometimes they ask you on this photo, do you want to give a name? And then give a name. And then I think that's how I'm wondering that behind the scene, it's realizing all these photos, and then when you give a name to that photo, it's doing this.
You do a lot of things. It's hard to tell exactly what they do without talking to the team. But see, all of these technologies are the same. None of these companies are doing anything revolutionary. Good thing is that, like this paper, it came from, who published this paper? I believe this is OpenAI. This is an OpenAI paper, I'm pretty sure it's OpenAI. Right?
Yes,
Yeah, it's an OpenAI paper. So all of these people, see, there's an interesting paradox in our field, which is that, yeah, at the bottom it must say, equal contributions OpenAI. That's right. There's an interesting paradox, a tension in our field. All the researchers love to publish their work. And they do a very good job. All the companies want to hide their work. Right? And yet they can't do without researchers. And researchers want to be open. So you have this big continuum. For the longest time, the tradition has been to be very open about research. And people compete, companies compete on the quality of their implementation.
Yeah.
Right. But recently, the trend has been a little bit disturbing. For example, some of the papers that come out, like for example, the description of how GPT-4 works, you have no clue, right? You get some little hints. You look at the Gemini, that is a masterpiece of not telling anything. The Gemini research paper. It has one block diagram. It says input goes in, magic happens, output comes out. Right? So, right. So I don't know. Right, yeah. So it's I don't know, like, you know, if you're an engineer and you're doing research in this space, you have to, at the end of it, companies feed you. So you bow down to them. But at the same time, the basic urge of engineers and researchers is to be rather open about their research. That's how ideas move forward. That's how progress is made. And I don't believe any of these common things that happen in Google, etc., are anything special. They all are using the same ideas, different variants of the ideas, and moving forward. So the community so far has been fairly open. Most ideas are known. Though sometimes you do worry if it is always true. If some ideas are not being talked about, who knows? So that's that.
So I understand correctly, right? So the transformation from the text to the film representation and the picture to the there could be doing two different things, right? The text to video representation to the bird and film to the video. And then the matching of those two is done by the weight value.
Yeah, that is right. So you could do, for example, you could have a bird to create your sentence embedding, but then what will happen? The loss function will force both of them to learn all the weights and biases in both of these networks to change. And that's the point it's making. That is literally the point you're making. Here, look at this. You can have whatever you want to encode the image. You can have whatever you want to encode the text, so long as ultimately they feed into a loss function. This is your loss function here. Loss function is defined over this. What will it do? What is the next step after computing the loss function? It is, if you go back and look at what we just drew, where are we? Somewhere we wrote that down. Oh, I seem to have lost where I wrote it down. But what is the next step after loss function in the learning loop? It is, say that.
Updating the
Back propagation is back propagation. Back propagation through what? Through both of these networks. So both the networks will be forced to learn. And that is why the use of the word jointly. Do you notice that they use the word clip jointly trains? And let me underline this sentence here. It jointly trains the image encoder and the text encoder. How does it jointly train? Back propagation will push the gradients of through both of the networks, and both of them will have to take a step of learning. Right? So you go pick your text encoder architecture, you go pick your image encoder architecture. So long as they are open, the weights are not frozen. So long as they are open to learning, both of them will learn jointly, and they will learn to align in the embedding space, isn't it? And that's the beauty. That's what this paper is saying.
What's there on the right side of 2 and 3?
So what happens is that create a dataset classifier from label text. After that, you can use it for, like you can use this for classifying, create a dataset classifier from label text. What it means is that you can take an image and you can then use it. So think about it this way. You have an image and you want to know what is this? Right? So the right hand side is, I want to know what is this? What can I do? I can take a text, a photo of a, you see this blank spot object. And in that object, I can now feed in each of the labels of the classifier. Suppose you want to ask this picture, and that's why you call it a zero-shot classifier. See, let me explain that in a more careful way. But one moment, guys, I'll do my reading glass here. See, guys, just observe me. Pay attention to me here. Suppose I tell you, I give you an image, and I say, is it a zebra or a giraffe? You can say, now wait a minute. I don't have a trained classifier for zebra against giraffe, right? So you haven't trained a classifier just for zebra and giraffe. But when you say create a zero-shot classifier, means zero-shot means what, guys? In the industry, when we use the word zero-shot, no training at all. Can I end up with a classifier, magically produce a classifier without any training whatsoever, right? And that is supposed to be one of the desirables these days. Zero shot is all the rage. How do we do that? So they show how to do that. You said, okay, did you say zebra and giraffe? Easy. I will create a sentence. What is the sentence I will create? A photo of a, so suppose I'm doing zebra versus giraffe. These are the two things, right? A photo of a zebra, a photo of a giraffe. What will happen? Both of these will become vectors, right? H zebra, H giraffe, isn't it? And then I'll also get an image encoding, right? And this image will become H. Well, it turns out it was a dog in this picture. But let's imagine you want to confuse it with a zebra, right? Picture. Let me just call it picture. Now what happens? This picture will also end up in the vector space somewhere, 3 vectors. So now can you connect the dots from here, guys? If I want to classify, how can I easily classify? I just see this image. Is it closer to the zebra vector or is it closer to the giraffe vector? Isn't it? And I can answer it. And therefore, the beautiful thing is you just created, once you have CLIP trained, CLIP can act as a zero-shot classifier for all such situations. Isn't it? Do you see the power of it, guys? That's it. You have a zero-shot classifier.
So this is the downstream task.
Downstream task that it can solve. Exactly. It's a downstream task. So, guys, these things.
So even if it is, say, for example, the picture, the actual picture had a horse.
Yeah.
And it will say it is a zebra.
Yeah, because zebra is the closest thing to a horse. Giraffe has a far longer neck.
So on a lighter note, I think would struggle to classify abstract art. Because this would text and associated with abstract art.
Yeah, yes, that's right. So, yeah, go ahead.
From the process standpoint, let's say you mentioned that some of these systems they use the alt text to map this text to the image. After that's done, what if the alt text changes? What is you have to run the whole process?
No, you don't. Scraping the web is not a trivial exercise. It's very, very hard.
Yeah.
Right. People like Google do it at industrial scale. Open source effort is the common crawl. Right. And you see, good news is data exists. Bad news is very noisy and it's expensive to scrape.
Right. So in a smaller data set in the enterprise, if there is mistakes in labeling, whatever, then what do you do?
See, the law of large numbers comes in. Good thing is that the machine learning algorithms, right, inherently, they don't see the loss function. You never try to reduce to 0. You try to minimize the loss always, right? So you just say that assuming that the data is mostly correct, that's the wording people use. Assuming that the data is mostly correct, how can I train the model? Yes.
Yeah, and then so the follow-up to that is like if you train the model, assuming the data is correct, then you find out that there are some discrepancies in the data. Then you go through the retraining process. And
you can, and in fact, that's a very good segue into the blip and the blip 2 paper. So let's hold that thought. One of the contributions of blip, the next paper, is it found out not only a way to find the captions, learn from the captions, but to correct the captions and improve upon the captions. Yeah. But let's keep that surprise for the next architecture.
Ashok, can I come in for a question?
Yeah, guys, let me take the remote question. Yeah, go ahead, Anzu?
There's a
Yeah.
large,
I'm trying to understand what is the overlap with the CNN-based networks like mass CNN, YOLO, post-estimation, segmentation, background, foreground images. So is CLIP basically derivatives of CLIP basically taken over all that, or it's still a mixture of both?
No, so today, see, in the NLP world, transformers are the supreme emperors, pretty much, right? They have taken over quite a bit. And RNNs are still there, but they're sort of a little bit in the background. They're still being used, but not so much. In the computer vision space, visual transformers are still making their inroads. See, all of these things have just happened in the last couple of years. So CNNs are still going strong. YOLO is at, I believe, at this moment at V8, YOLO, or V5, forget. YOLO V8, I think. And there's a YOLO NAS, which has come up after that. CNNs are still doing strong, and visual transformers are gaining ground. That would be the way to position it. So, for example, even for image segmentation, if you look at papers like from Facebook called Segment Anything Model, SAM, and Grounded SAM, they are transformer-based image segmentation. And the whole question is, today, YOLO is used most in production, right? And it is CNN based, but SAM and these things, these are groundbreaking research that is coming up. And over time, I suppose they'll mature and they'll start taking over.
I see. Okay. And for things like post-estimation or like background, foreground, and the video, are they also within the domain of CLIP or derivatives of CLIP?
Oh, no. CLIP is no. CLIP is, just think of it as just a semantic embedding machine. They're not in CLIP, but they're within the domain of transformers. And we will cover it in this workshop. We'll do all that.
Okay.
So CLIP is very specific. It says, hey, you can not only do semantic embedding of text, here is a way to do semantic embedding of images. Right? So images can be treated as that's all it says.
Oh, so it's not like, I mean, I think I've heard of CLIP segmentation, for instance. Is that like not derivative of CLIP, or they're completely different things?
No, they're different things.
Okay.
Different parts.
Yeah, thanks.
And we will get there. We'll get there. In fact, segmentation, see, we will start with the segmentation using, for example, the classic of segmentation is the UNet. We will cover UNet, and that is a CNN-based architecture. And then we'll move forward with that.
Thanks, Asim.
So, all right, guys, we have taken a little bit more time than I had initially planned. So for the blip and the blip 2, we'll have to move a little bit faster, and we have to cover, or maybe I could push it to next time. What's the time now? It's 12:20. Would you guys like to take a break before I do blip, or would you just want to steam ahead? Steam ahead? Okay. So let me stop this recording. And any more questions on clip, guys?
Just one quick one. So can this also be applied to the audio encoding?
Very good question. So Bhavin asked, can it be used for audio encoding? And would somebody like to venture a guess? Can this clip be used for a video encoding, or this sort of argument be used for video encoding?
Yes.
Yeah. And how would you do that?
Convert the audio to video?
Convert audio to video? No. Convert audio to
text.
Representation.
Yeah, there are two pathways that
Images.
you could do.
Convert audio.
Images, exactly. There are two pathways. Convert an audio to text or audio to a MEL spectrogram, which is an image, right? So you could do, for example, Whisper, any of the text to speech to text will convert it to text. But I think today you do a MEL spectrogram and you can embed it. You can do thermal image embedding. You can do like depth image embedding, very common. So people are taking images. And by the way, these things have far-reaching consequences today. in the medical domain, this multimodal learning and the fact that we can cross encode or jointly encode images, you realize that when you start thinking of X-ray images and MRIs and CT scans, these things have far-reaching implications, because guess what happens to every MRI image? Associated with it is a textual description. Right? Now, remember, CLIP is a baby. Like today, we consider CLIP almost like a granddaddy of all of these ideas. Right? It is both very recent and rather ancient. It started the whole field. There's a lot of new things that have come up that facilitate that, building upon these ideas. But the fact that we can jointly embed text and images and a lot of valuable information in many domains, like in medical, every X-ray has a radiologist's notes. You realize that, right? And interpretation associated with it. Just think of the implication of that.
So what you're saying is every image goes up, someone is speaking out or typing their notes about that image. And eventually they'll.
Yeah, eventually I can bring up an image and I can therefore pick up the most similar descriptions of that image. And as you will see, in fact, I don't want to scoop or steal the thunder from the next paper, because that's where it is all leading to gradually. When you see where we are heading, it would be, I would imagine that at the end of the day, you would come out with a completely different understanding of how far technology has gone. So anyway, but enough for the clip. So any specific questions on clip before I close? Was this useful?